Page 6. Making an executive decision on page 6. Since the bottom is riddled with errors anyways and would have been too confusing and we really never got to that part, we're not putting this one on the exam. So we'll just leave that one blank. So coming back up to the top, it's another stoichiometric problem. Don't let the 25 halves oxygen fool you. You could convert that to 12.5 if you had to, but let's just see if we really need to. Use the following reaction. Okay, it's balanced. It is a complete combustion to determine A, how many grams of CO2 are formed when 35 grams of octane. So we know what we're going to start with is this, and they're only asking us about this. So first things first, we're going to start with 35 grams of octane, C8H18. What would that weigh? 12 times 8 is 96, plus more 18 more is 114, 106, 114. 1 mole is 114 grams. So when I look at that, grams and grams don't cross off, so I got to reset that back up. 114 grams, that way grams and grams will cross off, is 1 mole. 35 divided by 114 is a whopping 0.3 moles. If we had 1 mole, we would get 8 moles of this. Well, we don't have 1 mole. We have 0.3 moles. So we're going to get 8 times as much. 0.3 moles times 8 moles comes from 1 mole. That's the mole ratio is 8 to 1. It's going to be 2.4 moles of CO2. So how much does 2.4 moles of CO2? I put that there. Use that to find this. 2.4 moles of CO2. Let's see. 1 mole weighs 32 plus 12 is 44 grams. We should get about 105.6 grams CO2, theoretically. How much energy would be released? We're burning something. Lots of energy is given off. For every 1 mole we burn, we're going to get 5,483.4. I wouldn't really call it negative. They put that so that we know that it's being released, but that's how much the way it's question is. The way the question is worded is how much energy is released. So I don't really have to go back to this 35 grams. I've got this here is it's 0.3 moles. 0.3 moles of C3H8. And let's see, 1 mole of C3H8, according to this balanced equation up here, will release 5,483.4 joules. Kilojoules, actually. Let's see, moles and moles cross off. It'll leave me kilojoules. So I simply take that number, 5,483.4 times 0.3, 1645 kilojoules. That's how much is going to be released. We just use this as if it's it is part of the balanced equation. For every 1 mole of octane that's burned, you'll get 5,483. The next one's calling for a Bohr's model. Not a lot of points, but it's something that we dealt with. A Bohr's model is a circle that represents the nucleus. It could have concentric circles, but we ended up tending to not need them, and all we have to do is just use just a little side of that. So I can get rid of all this and all this and all this. Inside there, I'm going to need to know how many protons and how many neutrons. And then out here in these shells, I'm going to draw shells that have how many electrons are in each shell. What are we dealing with? We are dealing with phosphorus. I could go look at the periodic table for phosphorus and find that it's number 15, but really the way they framed this for me, all I have to do is look at this. Phosphorus 15 with a 31, usually it's written over. That means that, well, all I'm going to redo this. Circle. How many protons? All phosphorus has 15 protons. This number does not refer to how many neutrons. It's the total mass of the nucleus. So if I do a 31 minus 15 to get 16, all the rest of the weight, 16, is in neutrons. Of according to our periodic table somewhere, it says that the number of in a normal neutral atom, the atomic number is the number of protons, and it's also the number of electrons, but we have to put them in the right places. Do we remember how many the first shell holds? It only holds 2. It's like the first level of the well or the bottom of the well. The second shell only holds 8. These are electrons, electrons. So what's left? Well, let's see. I need 15 total. I got 10 showing. I'm going to need 5 more. That has 5 valence electrons. Next one, an unknown metal has 2 isotopes, just 2, that's nice, based on mass spectroscopy data. One isotope is 50.69% abundant and has a mass of 78.9. I liked the new way that I learned on the video. If I have one that has a, it doesn't matter which order I do this, but if I have one that has a mass of 78.9183, and that is 50.69%, I'm going to add that to the other one, which has a mass of 80.9163, and I multiply that by 49.31%. That's also in parentheses. When I add those two up, then I'm going to divide it by 100 to get rid of, to translate that percentage to get a number. This is where you might want to use your view, a scientific calculator, and I always struggle with these, but I'm going to give it a try. Parenthesis 78.9183 times 50.69 end parenthesis plus parenthesis 80.9163 times 49.31 end parenthesis. Now I should be able to divide by 100 and I should get a weird number. And then a little magic occurred. I should have pressed the equal button after the addition that I done and then divide it by 100, and then I'll get 79.9. That would be the atomic mass, the average atomic mass. I'm getting 79.90. Should go look on the periodic table. Is there something that has one of 79.90? There it is. It's bromine. So if I identify this, it will be bromine. That'd be grams per mole, but you could just leave it as 79.9. Okay, why does the atomic radii decrease? So this one's asking us about, the first question is going to be about atomic radii as we go down the chart versus over. As we go down, we have an increasing atomic radii. And if I was just to draw a little tiny little models, Bohr's models, it's because as we go down, we add another shell. The first one only has one valence, one shell. The first is its valence. The second one has 2 shells, and so forth. In fact, the period number indicates how many shells. So the radius as we go down, as we add more energy levels, the radius increases. Biggest one would be at the bottom. But as we go from left to right, they're all going to have 2 shells, every single one of them. I'm going to just pick, I'm going to pick this. As we go from left to right, every single one of these are only going to have 2 shells. But the, like this is number 3. So when I drew this, how much the protons are what kind of give it like gravity. If I have 3 protons, they can't hold on to those 2 shells as tight as 4 protons. A little bit closer, and if I go jump down here to 5, 6, 7, 8 protons are going to suck those 2 shells even tighter. 9 protons even a little tighter. So it's like the gravity, the attraction from the nucleus, the more protons we have, the closer it keeps the electrons. When we get out to here, the 10 protons are going to be nice and close. So as we go from left to right, we get decreasing atomic radii because the bigger nucleus pulls the electrons closer. Next topic, so if I was going to write that on here, what might it sound like? Why does atomic radii decrease moving left to right, but increase moving down a group? It increases, I'm just going to read it, it increases going down because there are more energy levels. But it decreases from left to right because as the nucleus gets bigger, it pulls harder on the electrons and pulls them in tighter. The other topic is ionization energy, and they're kind of tied. Ionization energy is how much energy does it take to remove an electron. So we'll just talk about the first, ionization energy. What do we find out for ionization energies as we go down? I didn't have much room, so we have decreasing ionization energy. It's the opposite trend. It's like inversely proportional to the atomic radii. Decreasing ionization energy is what the question's going to ask us. Why does energy increase moving left to right, but decrease moving down? Well, when we look at how far away this energy level is from that nucleus, it's going to be easy to steal it. It's like the nucleus is sort of pulling it in, but this electron is so far away that it's easy to remove, versus this one is going to be a little bit tougher because it's so close to the nucleus has a tighter grasp on it. That same thing applies as we go across. Because this gets smaller, we're going to have an increasing ionization energy. It'll be harder, increasing ionization energy. As that nucleus gets tighter and tighter, it would be harder to take that away because it's very close to the energy that's holding it in tightly. If I'm going back to read this one, why does ionization energy increase moving left to right, but decrease moving down? I wrote, it takes more energy to steal electrons if they are closer to the nucleus. As the radius gets bigger going down, it is further from the nucleus and takes less energy. As the radius gets smaller, going left to right, it takes more energy. And like said, we're crossing off this last one. That should do it.